All right, thank you very much, and thanks to the organizers for providing me this opportunity to talk about some of the work that we've been doing. So I'll follow up a bit on what Andrea was discussing in terms of how we can learn more about cosmology from the Lyman-alpha forest at these very high redshifts as a sort of precursor to what we hope to achieve with the next generation spectroscopic surveys that will focus also on galaxies at these high redshifts. And where I would like to start is I would like to remind you how we usually like to do cosmology. We have these very excellent measurements from the cosmic microwave background that George introduced, and they give us an immensely powerful way of testing the preferred model of lambda CDM down to lower redshifts. And we've been doing this with galaxy surveys for 2 decades. We've been doing this with intergalactic mediums, a slightly higher redshift for about a decade now. And what we'd like to see is where something breaks. And we've been able to do this with intergalactic medium, not only in sort of this expansion of the BAO that Andrea was talking about, but we've also been investing quite a lot in trying to understand small-scale fluctuations in this opacity in the quasar spectra that we observe, in sort of how does the transmission along the quasar spectra correlate due to the presence of neutral hydrogen overdensities. And this is where we roughly are today. We are gaining information from the intergalactic medium at these high redshifts from 3-dimensional correlations using the BAO feature, and we are learning about the sort of formation or structure formation and impact of dark matter models on small scales from this 1D statistics. And what I'm going to mostly talk about now is how we can expand both of these avenues and where we are headed with the Lyman-alpha forest cosmology in the next 5 to 10 years. So first of all, with this small-scale clustering, while we are really sort of probing the 1 megaparsec or even smaller scales, what I would like to remind you here is that we are not seeing galaxies at a 1 megaparsec scale. We are really sensitive to overdensities of just a few. Basically, at high redshift, we are sensitive to mean density of the universe in the filamentary structure between the galaxies. So this is a very, very different environment that we are probing with these clustering statistics. And it is one of the key features that allows us to extract a lot of the information out of these small scales, as we believe that we can accurately model various systematics that were just discussed due to baryonic physics, because the baryonic component or baryonic physics of the intergalactic medium, while complicated, it's still much less complicated than galaxy formation physics. And also, while these big surveys like DAISY, and I'll come back to these big surveys, are beginning to be limited by systematics in the 1D clustering of these small scales, this is not true for very high resolution spectra that we have from CAC or VLT UVAS, where we are really limited by a small number of statistics, small number of quasar spectra with high fidelity observations that we can use for this purpose. In fact, what I'm going to highlight is some results that we recently published that were based on new high redshift data from Elisa Boera and George Becker. This was really taken from these very high resolution spectrographs, targeting quasars at very high redshift so that we have Lyman-alpha forest coverage from redshift 4 to 5. It's increased the sample size by a factor of 2 that people have used before, and this still means 15 quasar spectra. 15, not 50, but 15, and these are the measurements up top, that I did not show, but so I'm supposed to, all right, so these measurements up top here are the measurements of the 1D clustering from only 15 quasar sightlines, and this is really allowing us to get to unprecedented precision on the different dark matter models that we can extract from the Lyman-alpha forest. And because we are probing these very, very small scale physics, we have to rely on cosmological simulations to do interpretation for us. We cannot rely on semi-analytic or analytic models anymore. And for this purpose, we have developed together with collaborators a suite of simulations that covers different astrophysical scenarios, different ionization histories, different thermal states of the IGM, as well as different patchiness of the ionization for the first time. We've covered different numerical effects like resolution in the simulations, as well as different evolution of the mean transmission in the universe. together with different models of dark matter that we then propagate through Bayesian inference network to get constraints on these parameters in the model. And this is not something that's been done for the first time. This is a result of almost 2 decades of effort, some of which was started here at the IOA with Matteo Viel and Martin Henold. And it's really trying to use this Lyman-alpha forest small scales and pushing to smaller and smaller scales. We're really going below sort of 100 kiloparsecs in co-moving size, where we're tracing down the amount of fluctuations in the intergalactic medium. And this is providing us new constraints on this particular type of dark matter, warm dark matter models. What is sort of important to note are these small details that are sometimes glossed over, but when we include our improved modeling, this only slightly changes constraints. So these are very, very robust measurements all of a sudden. And they're also very, in some sense, driven by the amount of statistical power that we have in the limited sample of quasar spectra. If we actually compare the analysis we've done in this work to a similar analysis with similar choice of modeling and similar choice of data cuts to previous such analysis, we have almost a factor of 2 improvement in the parameter estimation that we're getting. Now, Lyman-alpha forest is, of course, not the only way to constrain dark matter, and I think throughout the week we'll hear about some other works. I think Kier will talk also about some other works just after my talk, but it's definitely Lyman-alpha forest putting constraints on different dark matter properties out there, and it's pushing our ability to constrain the amount of structure in the universe to very, very small scales. And this is what we would essentially like to understand. Is lambda CDM really valid all the way to very small scales? Does it break somewhere? Do we see some effect of a different non-cold dark matter model? And because the parameter space that we can probe is so vast, we really have a daunting task at our hands, but we are hopeful that we can really push this further. And what's more, with these new data sets that are coming out now, for the first time, we're hoping that we'll be able to start to distinguish between different dark matter models and not only talk about, for example, whether the dark matter is light or heavy, but what is also the production mechanism of this model. And on the other side, we would like to say something about going leftwards on this figure, where I'm showing the matter power spectrum, the linear matter power spectrum on y-axis and scale on the bottom axis, where large scales are to the left. We would also like to probe, we would like to use Lyman-alpha forest to probe this large-scale regime. And this is sort of the remainder of the talk that I would like to give, is trying to bring Lyman-alpha forest clustering on large scales closer to what is being done in galaxy clustering community. In particular, we would like to extract information beyond the BAO, beyond just the position of the BAO scale in this clustering statistics. We would like to use the full shape information of the power spectrum of a given tracer that we measure. And this is where we really are right now as of a few weeks ago, and I will show some exciting preliminary results. I would like to note, though, that in galaxy clustering, there are many methods how to actually extract cosmological information beyond the BAO using redshift space distortion or Alcock-Pociński tests, and some of these have also been developed in the Lyman-alpha forest community by Andreu and his group in Barcelona. I will mostly focus about is a different aspect, which is really measuring the 3-dimensional power spectrum of the Lyman-alpha forest transmission and Lyman-alpha forest clustering. And these are measurements that we've obtained with Roger Lebelsun, who was a student here only a few years ago with George. We've measured in EBOS survey the monopole and quadrupole of the Lyman-alpha clustering. This is at redshift 2.3 versus what galaxy clustering typically measures at lower redshift of around 0.5. And we are now in the process of using an EFT-like, a modeling, an analytic modeling technique that people use to analyze galaxy clustering that comes from perturbation theory and apply the same kind of methodology, the same kind of language to the Lyman-alpha forest measurements. And this is a paper that will be coming out very shortly. And I can show you some preliminary results. So typically people like to extract a couple of different parameters, but I will focus on these two here. We are only fitting for now flat lambda CDM, and we're trying to understand how consistent is the picture coming from Lyman-alpha forest clustering. This is really the first such analysis being done. And in this space of sigma 8 on y-axis, where sigma 8 is telling us something about the amount of clustering at around 8 megaparsecs, versus omega matter, so the energy content in matter, we are really in sort of this vertical, vertical green vertical green band is showing our Lyman-alpha results that are still in progress, but we believe that this result is mostly robust now, and only some minor changes may be coming. I would also like to mention that this is EBOS data for now, and we have DAISY year 1 and DAISY year 3 data to analyze, so things will improve. We also hope to improve beyond sort of relying on some prior choices for bias parameters, which is something related to the thermal history and thermal state of the IGM. We're still sensitive to this right now, but with future work where we'll be able to include various cross-correlations of the Lyman-alpha forest with, say, quasars or CMB lensing, this should also be alleviated. And here I will conclude. I will just like to sort of stress a couple of points. One is that Lyman-alpha forest is really coming into its own as a tool to be able to measure not just BAO, not just 1D clustering, but everything from small scales to large scales, expansion history, and sort of growth information. And this is coming from various different techniques that are being developed as we speak. On small scales, we are really limited. If we want to push to very, very small scales, we are limited not by these big spectroscopic surveys, but by an amount of high resolution, high quality spectra that we have from very large telescopes with extreme resolution. And on large scales, we're really gaining momentum in these different techniques from which we can extract more cosmological information and be sort of not just competitive with the galaxy clustering, but complementary in terms of redshift coverage and scale coverage. All right, thank you.